if we assume that xi is 0 meters per second where she started, xf in this case will have to be 50 meters, okay, in front of her. Will she be able to stop before hitting the obstacle? Now, the fact that they mentioned the reaction time, that means as soon as she sees that, she's not going to press immediately on the brakes. So the car during that time of indecision, or she's trying, the car is moving at a constant velocity of 20 meters per second during that time. So I'm gonna always, I like the idea of solving problems by using diagrams. So I'm gonna draw a diagram here, and then what I'm gonna do is I'm gonna match the diagram with a graph underneath here that would kind of go hand in hand with it. Watch carefully what I'm doing here, how I'm matching, areas on the graph. This is time measured in seconds. This is the velocity measured in meters per second. I always like to use the velocity versus time graph when I'm solving problems like these. And if you're not sure why, go back to my previous kinematics videos and you'll make sense of why I did that. Okay, so in this case here, a time ti equals 0 second, and this is a time, we're going to call it time react. This is time final react, meaning the reaction time, and then and in this case 0.80 seconds, and then this is the ultimate final time here. The same thing, this is the initial position, which is equal to 0, and this we're going to call it x react, meaning the xf react, the final position after the reaction time, and then this is the ultimate final position right there. This one is going to be equal to 50 meters. I love the way I'm writing. What else do we have here? So in this case here, this portion is going to correspond to delta x react, and then this portion here we could call it delta x stop, because that's when she's initiating the stopping with the car. And then let me see here, what else could we, and of course the change in time here we could call it delta t stop, and then this could be delta t react. Oh, I didn't mean to play with that, that's kind of cute. Okay, delta t react, you get the gist there. Okay, now at this point I'm going to change this to green, and I'm going to show that the velocity in this case is constant, and it is corresponding to the initial velocity Vx sub I, which is equal to 20 meters per second. And then from that point on, she's applying the brake, and it's going to fall off all the way. Well, actually, that's not accurate, so I'm going to have to erase this here, because we're setting the point actually that it is, let me see here, I want to match this right there, so I would be consistent. Okay, so this here would be corresponding, to the graph of the stopping. Notice how this is a straight line with the negative slope, so that means it's the slope which represents the change in the velocity over the change in time, therefore it's an acceleration of some sort. Okay, now how am I going to approach this problem? Again, I don't like to hunt for formula or look for formulas. Instead, I'm going to work with a few things here. So I'm going to figure out the area under this portion, and then I am going to figure out the area in, maybe let's draw this with a different color just for the sake of it, and then I'm going to figure out the area under here. Okay, and in this case, if you guys go back to the previous slides, you would know that this is some kind of a displacement, and this is also some kind of a displacement, except what kind of displacements are these? So this will be the displacement react, and this will be the displacement stop, because that's, corresponding to the region right here when she was trying to stop, while this one is while she's trying to react. Okay, now we're gonna use a little bit of geometry. This is an area of a rectangle, and this is an area of a triangle. So in the next page, what I'm going to do is I'm going to write, keep in mind that this is corresponding to delta T reaction, and then this corresponds to delta T stop, and this here, we already said this right there is the velocity, which is the height or the width if you're talking triangle or rectangle. So let's move to the next page, please. And here we go. I'm going to write down the relationships that we are going to get. So for the delta X react, okay, we are going to get the delta T react, okay, multiplied by the Vx. Remember, that's for the rectangle thingy. Okay, let's go back in case you don't remember that. I just would like you please to see it. So you see, I mentioned already that this is times this right there. Okay, let's go back. Okay, so the delta reaction time is basically the 0.80 seconds, and I'm multiplying it by the initial velocity, which is 20 meters per second. Beautifully, the seconds and the seconds will cancel out, and that gives me a delta X for the reaction corresponding to 16 meters. Okay, now I need to move to the second part, which is delta X stop. Well, delta X stop, it's the area of a triangle, so it should be half delta T stop multiplied by the height, which is again the Vx sub I. Interestingly enough, I know this, but I don't know that. So I need to determine that. Well, this is again where the geometry is so cool. Why do you think I taught you the idea of slopes and areas? So the slope of the green line is going to be the acceleration along the x. Let's go back here. It's the slope of this line right there. Okay? So it would be delta V, meaning the change in the velocity over the change in time. So what that means is it's going to be equal to delta V stop divided by delta T stop. Okay? The delta V stop, it would be V final minus Vx final minus Vx initial divided by the delta T stop, which I don't know, and I'm going to be trying to determine it. Okay, the delta V final is going to be 0 meters per second because it stops. We hope the car would stop. And then minus 20 meters per second, which is and I'm dividing by the delta T. So that would give me then, well, wait a second. And also we know they told us that the acceleration is negative 6.0 meters per square second. So that means negative 6.0 meters per square second is equal to negative 20 meters per second divided by delta T stop, delta T stop. If I exchange these, and believe me, you can do that, go check with your math teachers about this, delta T stop then will be equal to negative 20 meters per second divided by negative 6.0 meters per square second. Look at the beauty here. The meters and the meters cancel out. The second will cancel out with 1 of the seconds here. And then here's the beauty. You're going to end up with 1 over 1 over second. Well, that's the reciprocal of 1 over second, which gives you the seconds. But I'm not done yet. Notice the beauty here. The negative and the negative will cancel out. You end up in the end with delta t stop being equal to, let's see here, 20 divided by 6, that's 10/3, and then second. So now look at this. We've got this. We can substitute it here. Therefore, we can get 1/2 times 10/3 second multiplied by the Vx, which is this Vx here, Vxi that is, which is 20 meters per second. Beautifully again, second and second will cancel out. The 2 and the 20 will cancel out, and you end up with 10 up there. So that gives me 100 over 3. So this implies that delta x stop is going to be equal to 100 over 3 meters. Now, pay attention please everyone. That means the combination of delta x react and delta x stop added together, let me go back a couple of slides back, meaning this plus this has to be equal or less than 50. Preferably less than if we don't want her to hit the wall. So let's see if that's true. Let's see if that is true. So, delta x react, added to it delta x stop is equal to 16 meters plus 100 over 3 meters. The 100 over 3 is almost equal to 33.33333 whatever. So that means 16 meters plus 33 meters. If I go with 2 sig figs, that would give me 49 meters. Whew! That's less than 50 meters by exactly 1 meter. Therefore, she will stop 1 meter short of hitting the obstacle. Cool. And this is Sidi Naajee signing off. Thank you.